Alright, starting chapter 10, chapter 10, 10.1 is parametric functions. Please focus. So in this chapter we're going to deal with vectors, we're going to deal with polar functions, but in 10.1 we're dealing with parametric functions. So parametric involves the parameter time or variable time. And just kind of follow my notes here. dy dx equals, we've done this before quite a bit, so we know that the derivative, like if you're given like t squared plus 4 and y equals sine of t, we can find the derivative or the rate of change by finding the derivative of the y with respect to time over dx dt. So we just figure it out. In this case it would be dy dt would be cosine t over dx dt is 2t. So that is our dy dx. So if we call that y prime of t, that's our dy dx. What happens if we find another derivative? So let's do the second derivative. So it would be the derivative of y prime of t. Well, we're finding the derivative of y prime of t with respect to x. So using the chain rule, it would be the second derivative, y double prime of t, times the derivative of the inside, because it's implicit differentiation because you're using different variables. So the derivative inside is just dt dx. Okay, so it's y, so it's the second derivative in terms of time times dt dx. Well, we won't know what dt dx is, but we do know what dx dt is. So our dx dt in this problem would be 2t. So instead of just multiplying by dt dx, I would divide by dx dt, because that's something we have. So if I was trying to find the second derivative here, we found the first derivative. Now find the derivative of that. Well, the derivative of this actually requires quotient rule, so bottom derivative of the top minus the top derivative of the bottom all over the bottom squared, and then we found the derivative of that, and then we have to divide by our original dx dt, which is 2t. Okay, so you find dy dt over dx dt, you get an answer. If you wanted to find a second derivative, find the derivative of whatever you have here, but then divide by the original dx dt. So if you had found a derivative here and you simplified the derivative, don't forget that the original dx dt was 2x. If you had a 2 on top and bottom, cross that up. Don't divide by like whatever the bottom is. You divide by the original dx dt, which is 2t. Alright, so I don't know if that makes sense or not, but hopefully it does, and maybe learn from any mistakes that you have in the assignment. Okay, so just cleaning it up, I have negative 2t sine t minus 2 cosine t over 2t over another 2t, so it's divided by 2t squared, and that's 4t squared. You could divide by 2 on top and bottom, but you get the picture. I guess I'll finish it. So negative 2t sine t minus 2 cosine t over 4t squared. You can divide by 2, so I have negative t sine t minus cosine t over 2t squared. That would be the second derivative. Alright, so I mean, that's a different example. I just made one up different than your notes. I don't know if I have to do the one that we did in our notes. So find the derivative I guess I will, as long as it's in front of me. So we've got our x and our y, so we're trying to find the first and the second derivative in terms of t. So dy dt over dx dt. The derivative of this over the derivative of that. Clean it up, you get negative t. Okay, so now we're going to do another derivative. So we have to do the derivative of that, which is negative 1, divided by whatever our dx dt was, which is negative 1 over t squared. So it's negative 1 over t squared, which turns out to be t squared. So that's our second derivative in terms of x, in terms of t, sorry. All right, arc length of a smooth parameterized curve. So if we're trying to find arc length and you've got parametric equations, this is how you do it. It's similar to what we did back in non-parametric equations. It's this, but since it's defined parametrically, you've got integral square root of dx dt squared plus dy dt squared. So an example, so if we're trying to find the arc length of the curve, here's our parametric equations. I've got x equals 5 cosine t, y equals 5 sine t, and we're going from 0 to 2 pi for our time. So our formula is the integrals, well, it'd be from 0 to 2 pi of the square root of dx dt squared plus dy dt squared. And we should be able to do it by hand. So negative 5 squared, 25, 5 squared, 25. We can pull out the 25, square root of 25 is 5. And then I've got sine squared plus cosine squared is just 1. So you're integrating 5 from 0 to 2 pi. So antiderivative 5t, 0 to 2 pi, you get 10 pi units. So what did we just find? We found out that x equals 5 cosine, y equals 5 sine. The curve created from 0 to 2 pi is 10 pi units. So what kind of shape is it? We go to mode, parametric mode. Oh, we got a lot going on there. Alright, so our x is 5 cosine t, our y is 5 sine t. I'm going to go window, I'll do zoom standard, and alright, so it looks like it's an ellipse. If you did a zoom, where's the square? There it is. So it looks more like a circle there. So it is a circle. Because these numbers are the same, that makes it a circle. So let's see. So what did we just find? We went from, let's go window, we're going to go from 0 to 2 pi. It's already 0 to 2 pi. So if you watch the way it's drawn, I guess I'll go draw, clear drawing, and then if I graph it, it'll draw it. So it starts here, it goes from 0 to 2 pi, which is right there. So we just found the circumference of a circle with a radius of 5. So if our radius is 5, circumference is 2 pi r, so circumference is 2 pi 5 times, so it's 10 pi, which is what we got when we integrated. So we could have used geometry. We used calculus to figure that out. Nice. All right. So surface area. So we've got arc length. The surface area equations are right here. Here's my little red notes there. So if I wanted to find the surface area parameterized function, if it's going around the x-axis, this is what we have. Around the y-axis, this is what we have. Notice around the x-axis is 2 pi y. and it's 2 pi x. Alright, so if we're going to find the surface area of what we just were working with before, which was the circle, we're revolving the top of the circle around. So if our whole circle is drawn from here to here, we only need our function to go from here to here. So it's a semicircle that we're going to revolve around the x-axis. So that's where 0 to pi comes from. So then we can just use our formula. Since we're going around the x-axis, we would use this top equation. Find our dx dt, our dy dt. Our y is just what the function is, 5 sine t. And then this will all become, let's see, it ends up being 25, and the square root of 25 is 5. You can toss that out. You get another sine squared plus cosine squared, which is 1. So all that becomes just the integral of sine t, and then you can find the antiderivative of that, and you end up getting 100 pi. So what did we just found? We found the surface area of for revolving a half circle or semicircle around the x-axis. We are finding the surface area of a sphere, and surface area of a sphere is 4 pi r squared. So it's 4 pi times 5 squared, so 100 pi. Using a geometry formula, we get 100 pi. Using calculus, we also got 100 pi. If we were asked just to find surface area of a circle with a radius of 5, revolving around the x-axis, we could represent this top equation not with parametrically defined functions, just in terms of x's and y's, and that's just y equals the square root of 25 minus x squared. So then we could use our old surface area equation. It'd be from here to here, so from -5 to 5 of 2 pi y, which is square root of 25 minus x squared, times the square root of 1 plus the derivative. Let's see, whatever that derivative is, 1/2 25 minus x squared to the -1/2 times -2x. So what's that? Negative x over square root of 25 minus x squared dx. If you worked on that for a while, you're going to eventually get 100 pi also. So another approach, this was how we would have done it before we were talking parametric equations. Just to show you that you do get the same answer. This is not something that I would ask your chapter 10 problems would ask you to do. Alright, last page of notes. So if we're asking to find a parameterization for a curve, let's say we've got a cubic and we're going between 1, 6 and 4, 81. The easiest thing to do is just say x is t. Okay, so it doesn't specify, it just says find a parameterization. So this would be easiest to just say x is t. So then all of these x's become t's, and we've got a set of parametric equations. Okay, and anytime you have equations, you have to say what's our interval of time. Well, our interval of time, we know we're going from 1 to 4 as far as x goes, but x is t. So we're actually going from t equal to 1 to t equal to 4, so from 1 to 4. We have our interval of time. Yeah, I don't know if this is in the book, but if you're given a circle, the x, if you're going to define a circle parametrically, x is always equal to r cosine t plus h, and y is r sine t plus k. So if we have this as our circle, our center is -4, 1. Our radius is the square root of that, so it's 5. That's the general formula for a circle. It's x minus h squared plus y minus k squared equals r squared. So in this case, our r is 5, and our h is -4, and r is 5, and our k is 1. So if you type that into the equation or just plotted the points, you would see that it is a circle. And we'd go from 0 to 2 pi, one time around the circle. Alright, last little skill if you're trying to find the integral of the square root of 1 minus cosine x. You can actually use the power reduction formula in reverse, or the power increasing formula. So Carl taught us that we have sine squared of u is equal to 1 minus cosine of 2u over 2. And we also know that cosine squared u is equal to 1 plus the cosine of 2u over 2. So these are the ones, the power reduction. You've got the tangent one, but you aren't going to use that as often. So in this case, if I have a 1 minus cosine of x, there it is. Alright, so 1 minus cosine x, that is close to this right here. So the 1 minus cosine, we need a 2 on the bottom, so we toss a 2 on the bottom, but then if you're going to put a 2 on the bottom, you better put another one out front. So we haven't changed the value of it, we just moved some stuff around. So I have that square root of 2 that you could put out front. Now we have the square root of 1 minus cosine of x over 2. Well, 1 minus cosine of x over 2 is close to this, 1 minus cosine of x over 2. Going here, it's going to be half of what this is. So if this is the cosine of 2u, this becomes sine squared of u. So if this is cosine of x, it becomes sine squared of x over 2, half of whatever we have there. So then, like I said, the square root of 2 goes out front. You have the square root of something squared. You end up getting the sine of x over 2. So antiderivative of that plus c. So you can change the inside into something squared, and then you can undo the squared with the square root. Alright, that is your 10.1 lesson. Yay!